There are three ways in which things can heat up, in which heat energy can be transferred. First, conduction. Viewed with this thermal imaging camera, hot areas look white, cool areas blue. So as heat energy transfers from the hot plate, the whole pan becomes red because of conduction. Here's another example. Put a hot block of metal on top of a cold block and see what happens. Conduction is the transfer of heat energy through substances from warm regions to cooler ones. The cold block is clearly getting hotter. Eventually, both blocks will become the same temperature as their surroundings. Metals are good conductors of heat, but some are better than others. Let's see which of these metal rods is the best conductor: aluminium, copper, brass or steel. On one end of each rod, a small rivet has been stuck with a blob of petroleum jelly. The other ends, furthest from camera, are all heated together with a Bunsen burner. The jelly on the copper rod melts first. Copper is the best conductor. Next, aluminium and then brass, leaving steel as the least good conductor. Most liquids are poor conductors. Take a test tube of water with some ice at the bottom held by a gauze. If we heat the water at the top, what happens? The water at the top boils without melting the ice at the bottom. There's little conduction of heat down through the water. Most gases are also poor conductors. Our imager shows that the air around this Bunsen flame is relatively cold. In fact, you can slowly bring a match right up to the flame before it will ignite. So, metals are good conductors, but liquids and gases are poor conductors. The second type of heat transfer is convection. Convection occurs by the movement of warm liquid or gas. Hot air above the candle rises, drawing colder air in from the right. Watch how the smoke is drawn down the tube. The rising hot air creates a clockwise circulation of air called a convection current. Adding a crystal of potassium permanganate to a beaker of water will show how convection currents can be created in liquids. Heating the right-hand side warms the water above the flame. This warm water then rises, drawing some of the purple dye across the bottom of the beaker. An anti-clockwise convection current is created. Convection occurs in gases and liquids because, unlike solids, they're made of particles which can move about. The third method of heat transfer is radiation. Every day, a vast amount of solar energy reaches the Earth, not by conduction or convection, but by radiation. This is the transfer of heat energy by means of infrared electromagnetic waves. The domestic grill also works by radiation. Everything around us takes up energy from radiation and also gives out energy as radiation. Remember, the thermal imaging camera records the infrared energy reaching it, not visible light. Different objects give out different amounts of radiation, depending on their temperature. Hot objects give out more than cold objects. But does the amount of radiation emitted depend on an object's surface? These two aluminium cans have different surfaces, one shiny, the other dull. The cans are filled with hot water at the same temperature. Will they cool at the same rate? The can on the right with the dull surface appears hotter to the thermal imager. It's radiating more heat. So the dull can will cool more quickly than the shiny one on the left. Bridge builders need to know that changing the temperature of a material changes its size. When solids get hotter, they expand. Here's a thick metal bar resting in a frame. Insert a cast iron pin through the hole at one end. Heat the bar for about 10 minutes. It expands and gets longer. Now tighten the nut to hold the bar in place as it cools. What will happen to the pin? As the bar cools, it contracts, it gets shorter. The increasing force on the pin eventually snaps it in two. Here's a metal ball and ring. At room temperature, the ball passes easily through the ring. Now cool the ring in liquid nitrogen. The cooled metal has contracted, so the ball no longer fits through the ring. Expansion of solids can cause problems. Railway tracks, for example, might buckle during hot weather, so expansion gaps or sliding joints are built into the trackwork. When heated, different metals expand by different amounts. Bonding a piece of brass to an equal piece of iron produces a bimetallic disc. Can you explain what will happen when these discs are heated? A candle is placed under a bimetallic strip. Can you work out what's happening? The bimetallic strip is working as a switch. Heat from the candle causes the strip to bend downwards. This completes the circuit supplying power to the motor. The fan then runs, cooling the strip, which bends upwards, breaking the circuit, and so on. This shows how bimetallic strips are used as switches in thermostats. Liquids expand more than solids. These flasks contain 3 different liquids: water coloured red, paraffin and methylated spirit coloured blue. Heat the flasks in a water bath and the liquids will expand. But will they all expand by the same amount? Methylated spirit on the right expands the most. A similar liquid is used in many lab thermometers. Why is it so suitable? Gases also expand when heated. This glass flask is full of cold air. Using your hands, warm the flask, dipping the end of the tube into some water. Bubbles soon begin to appear as air inside the flask expands, forcing its way out of the flask and into the water. Cool the flask and the water rises up the tube as the air inside contracts. This balloon is filled with helium gas. Cool it in liquid nitrogen and the gas contracts. Why does it begin to reinflate? This experiment looks at how gas volume varies with temperature. A flask of air is connected gas-tight to a glass syringe. The plunger of the syringe can move freely, so the air is at constant pressure. We're starting with the flask ice cold. As the air cools, it contracts and the syringe plunger shows a reduction in volume. To start the experiment, heat the air in the flask. Using the scale on the syringe, record the change in air volume over a range of temperatures. Here are the results: temperature in degrees Celsius and volume in millilitres. Plot them on a graph to find out how temperature and volume are related. Here are 2 identical pans. One pan contains 200 grams of water. The other, 400 grams. Everything is at room temperature. The pans are placed over identical gas hobs. Which pan of water will boil first? Obviously the one with less water. The pan with more water needs more energy for its temperature to change by a given amount. Its heat capacity is higher. So heat capacity depends on mass, but does it also depend on the substance being heated? Compare the heat capacity of cooking oil with water. Each pan contains 200 grams. Water on the left, oil on the right. As the pans are heated, the oil temperature increases rapidly. When the water starts boiling at 100 degrees Celsius, the oil temperature has reached over 130 degrees. For a given temperature rise, the oil needs less heat energy than water. We say that oil has a lower specific heat capacity than water. The specific heat capacity of a substance is given by the heat equation. Q is heat energy added to the substance. M is the mass of the substance, C its specific heat capacity, T1 the initial temperature, T2 the final temperature, so T2 minus T1 is the change in temperature. Rearrange this equation to make C the subject. For example, let's find the specific heat capacity of aluminium. This cylinder is a 1 kilogram block of aluminium. Place an electric immersion heater in one hole and a thermometer in the other hole. Note the initial temperature T1, 27 degrees Celsius. Connect the heater to an electricity supply and switch on. After 20 minutes, switch off and note the highest temperature reached, T2, 37 degrees Celsius. We know the mass m equals 1 kilogram. And from our experiment, the temperature difference is 37 minus 27 equals 10 degrees. So these figures complete the bottom line. Now the energy added, Q. Assuming that all the heat supplied by the heater is received by the aluminium, Q equals VIT, where V is the voltage of the immersion heater, 5 volts, I is the current, 1.85 amps, and T is the time the heater was on. 20 minutes equals 1200 seconds. So multiplying these together gives Q equals 11,100 joules. Finally, substitute this value into the heat equation, and our calculated specific heat capacity is 1,110. The units are joules per kilogram per degree Celsius. The actual value for the specific heat capacity of aluminium is 908. So our experimental value was quite close. Can you suggest causes of error and improvements to our experiment? Conduction is the transfer of heat energy through substances from warm regions to cooler ones. The cold block is clearly getting hotter. Eventually, both blocks will become the same temperature as their surroundings. Metals are good conductors of heat, but some are better than others. Let's see which of these imaging camera. Hot areas look white, cool areas blue. So as heat energy transfers from the hot plate, the whole pan becomes red because of conduction. Here's another example. Put a hot block of metal on top of a cold block and see what happens. Metal rods is the best conductor. Aluminium, copper, brass or steel. On one end of each rod, a small rivet has been stuck with a blob of petroleum jelly. The other ends, furthest from camera, are all heated together with a Bunsen burner. The jelly on the copper rod melts first. There are three ways in which things can heat up, in which heat energy can be transferred. First, conduction. Viewed with this thermal